Hi, everyone. Thank you very much for the introduction, and thanks for everyone to come along here today. So, as you heard, lots of my research and lots of my passion is really about prime numbers. And so what I want to do today is to talk to you about some of the reasons why I find prime numbers so fascinating, why I think they're important, and then to give a little bit of an idea of some of the work that I was involved in that was part of why I won the Fields Medal in my work on prime numbers. OK, so the key reason that prime numbers are really important to mathematicians is that they're somehow very fundamental to the structure of numbers when you multiply numbers together. And so they're often called the building blocks of multiplication. So what do I mean by this? Well, there's a general principle that goes way beyond just mathematics or science, that lots of the problems in today's world involve very complicated objects that have lots of different bits to them, but a very good way of trying to understand these big, complicated objects is to try and break them down into small pieces that you can understand individually. So, for example, if you're a chemist, maybe you're looking at complicated molecules, and you can understand a lot about a molecule by understanding the constituent atoms and how they join together. So if you're someone like me who is a number theorist tend to study properties of the whole numbers, and therefore you might try and understand properties of whole numbers by the constituent blocks. And there's a theorem, the fundamental theorem of arithmetic is what mathematicians call it, which says that every whole number can be written uniquely as a product of prime numbers. And this means that prime numbers are somehow the atoms of arithmetic. And therefore, lots of complicated problems to do with whole numbers can be broken down into simpler problems involving just prime numbers. The difficulty with this is that even these so-called simpler problems about prime numbers themselves often seem pretty difficult. And they turn out to often be related to very famous problems that mathematicians have studied and struggled with for hundreds or even thousands of years. The fundamental theorem of arithmetic is that every whole number can be written uniquely as a product of primes. So I'd like to give a couple of examples to demonstrate this idea of taking a problem to do with whole numbers and breaking it down into problems about prime numbers, which allows you to get some at least partial understanding about the original problem. And I want to take one example that's very much in the real world and the same sort of theme as Cliff's talk, and then another example which is related more to my world to do with number theory and whole numbers in pure mathematics. So one of the very important uses of prime numbers is in computer algorithms, and in particular in cryptography. And we've heard that one of the most important or most famous cryptographic algorithms is the RSA algorithm. And you don't need to know the details of this for my talk, but the key take-home is that this is a good way to communicate securely over the internet. You use things like this every time you buy anything using your credit card. Apart from a hacker could hack this and break internet security, at least with this cryptographic system, if you can turn a number back into its product of primes. So we have this theoretical result saying that every number can be written uniquely as a product of primes. And if you can do this for large numbers, then you can break lots of these cryptographic schemes. So, for example, you could take the number 449,623 and think, what are its prime factors? And maybe this isn't so difficult, so you guys can maybe do it in your head. It's 521 times 863. But when numbers are a little bit bigger than just a few 100,000, we believe that this actually becomes really difficult. So, for example, here's a slightly bigger number, and nobody has been able to write this number as a product of 2 primes, apart from the person who generated this. So someone generated this number by finding 2 prime numbers, multiplying them together, and then this is one of a set of challenge factorization problems. You get $75,000 if you can factor that in your head, all with a computer. And the fact that we believe it's difficult to turn this number into 2 prime numbers multiplied together is at the heart of why we believe the RSA algorithm is secure. And this is a common theme for lots of the variant algorithms that Cliff mentioned in his talk. We believe that going backwards is often a difficult process, but all of these algorithms are involving whole numbers being multiplied together, and so can be studied using prime numbers. But this question about turning numbers into its constituent prime factors is also a problem to do with multiplication. And even though we think it's hard, we can still try and tease out more properties by understanding more about prime numbers. And that quite quickly leads us to complicated theoretical problems about patterns in prime numbers. So Cliff mentioned as a side comment, I think, in his talk, that you have to be careful to avoid some bad cases of how you choose your cryptographic scheme when suddenly things that you thought of as being secure actually turn out to be pretty vulnerable. And so if you want to do the RSA algorithm, you find 2 prime numbers and you multiply them together, and that's going to be the basis of your algorithm. But if, when you picked one of those primes, it turned out that when you take away 1, that resulting number itself has lots of very small prime factors, and only very small prime factors, then it turns out that there's a clever way of factoring your original number. And this is known as Pollard's p-1 algorithm. So it's a bad idea to create these RSA numbers of 2 primes multiplied together if you're choosing a prime that, when you take away 1, it just has lots of different small prime factors. And again, this is using primes to study the problem. So to get around this, some people, it's not terribly advisable, but some people decided, well, I want to avoid this as much as possible, so I'm only going to use primes such that when I take away 1, well, if I've got it's got as few prime factors as possible, and so they're going to be as large as possible. So you can't have a big prime take away 1 and it be in another prime, because when you take away 1, it has to be a multiple of 2. So the next closest thing would be to say, well, if I take away 1, it can have a factor of 2 and then be a prime number. And that's sort of the hardest possible case from the point of view of this Pollard's p-1 algorithm. But and so this is an option even in some of the modern current uses of cryptography. There's still options to decide to use safe primes, even though, as I said, it's not really advisable these days. But if you're thinking about maybe using safe primes, a very natural question is, well, how often does this happen? If I'm going to have a scheme where maybe I'm thinking about finding a prime such that when I take away 1 and divide by 2, I get another prime number, how often does this happen? So this would be a really bad cryptographic scheme if essentially this never happened, because then your computer would just keep on trying to find one of these primes and it would fail. It would maybe be an even worse cryptographic scheme if it did happen, but it only happened occasionally, so some enemy could come up with this list of prime numbers such that whenever you take away 1 and divide by 2, you get another prime number, and then they would know that you're always choosing 1 from this list. Now, we expect that neither of these two things happen, but it turns out that this is actually a famous problem in mathematics that's essentially over 100 years old, and we don't know how to solve it. We don't know whether there's finitely many primes such that when you take away 1 and divide by 2, you get another prime, or whether there's infinitely many. We quite strongly believe that there's actually plenty of these, and there's infinitely many, but mathematicians have tried and failed for over 100 years to solve this problem. And this is the sort of problem that I like to talk about when I think about patterns in prime numbers, sort of pairs of primes that have some common structure. OK, so that's my example in the real world. It's internet cryptography, some of the most important cryptographic algorithms, because they're involving whole numbers being multiplied together, can be understood in terms of prime numbers. And we can try and investigate this even further by understanding some different ways of trying to factor numbers more easily. But then we start running into some famous 100-year-old problems about patterns in prime numbers. Now I'm going to switch gears completely and start talking about an example at the other end of the spectrum in pure mathematics. So my example is going to be maybe the most famous equation in the whole of pure mathematics, which is Fermat's last theorem. So Fermat claimed that there are no solutions to the equation a to the power n plus b to the power n equals c to the power n in whole numbers a, b, c, and n, with n being bigger than 2, apart from the obvious ones when you take one of a, b, or c to be equal to 0. So this was open for a very, very long time, and then famously proven by Andrew Wiles right at the end of the 20th century, who's one of my colleagues in Oxford. So the proof of Fermat's last theorem is one of the highlights of modern mathematics. The proof is a little bit too long for me to be able to fit it in the slide here. But this is an equation, very much in pure mathematics. It involves whole numbers being multiplied together, so we can still try and study it using properties of prime numbers. So, for example, it's a fact that if you want to prove Fermat's last theorem, you don't need to prove Fermat's last theorem for every integer n. It's sufficient to just prove it for every integer n which is a prime number. And it turns out that this is technically simpler. It helps with some of the structure in the equation, and this was almost sort of the first step in Andrew Wiles' proof of Fermat's last theorem. And in the same way that when we were thinking about the RSA algorithm and how we might try and play around with Pollard's p-1 algorithm and safe primes and things, you might think about how can we use further properties of prime numbers to try and make progress on this. And way before Andrew Wiles' work, there's work of Sophie Germain, who was a French mathematician, and she proved that if p is a prime such that 2p plus 1 is also a prime number, so if you have this strange pattern in primes, then there are no solutions to Fermat's last theorem with exponent p. So there's no solutions to a to the p plus b to the p equals c to p, apart from ones when ABC is equal to 0 modulo p, which is so-called the first case of Fermat's last theorem with exponent p. It was believed at the time that people would first solve the first case of Fermat's last theorem. You only need to think of n as being a prime number p, and you first of all deal with a case when none of the variables are a multiple of p, and then by some more complicated variation of the techniques, it was believed that you should be able to solve that in general. And based on ideas of this, she was the first one who kind of gave a systematic study of Fermat's last theorem and was allowed to solve many different instances of Fermat's last theorem. So this was maybe the first really sort of fundamental theoretical progress on Fermat's last theorem and the first sort of general mathematical progress for general exponents p. So she did really fundamental work, and this was over 150 years before Andrew Wiles did his work. But if you look at Sophie Germain's theorem, it's not totally clear how often this actually applies. Sophie Germain's theorem, at least as I've stated it here, would be a pretty rubbish theorem if there were no primes p such that 2p plus 1 was prime, because then it would never apply. So a natural question is, how many primes are there, how many primes p are there such that 2p plus 1 is also a prime number? And you might find this question somewhat familiar, because it's basically a reformulation of the question I had on the previous slide when I was talking about the example in the real world with cryptography, when I was asking how many primes p are there such that when you take away 1 and divide by 2, you get a prime number. It's these pairs, p and 2p plus 1, or you can change variables and call the big one p, and then be p and p minus 1 over 2. So here we have two extremely different examples, one related to hacking the RSA algorithm for internet cryptography, one related to Fermat's last theorem in pure mathematics, and they're both related to this question about patterns in prime numbers. How many primes P are there such that 2P plus 1 is also a prime number? Which is this famous 100-year-old problem that's still open, we don't know how to solve. So Andrew Wiles's proof did not go through Sophie Germain's theorem, and so he didn't answer this question, and this remains an open question even though we now know the answer to Fermat's last theorem. Okay, so we've seen already that there's a few different problems involving whole numbers multiplied together, and often these problems involving whole numbers multiplied together can be reduced down to problems about prime numbers that allow us new ways of looking at the problem and trying to study the problem. But quite quickly, when we start investigating further, we find that it leads to these questions about patterns in prime numbers where we don't know the answer, and mathematicians have actually studied these sorts of questions for decades or maybe hundreds or even thousands of years, and we're completely stuck. So how might we try and say anything about it? And what we would really like as mathematicians, what I sort of dream of having, is a sort of general method for trying to understand these sorts of questions about patterns in primes and the distribution of prime numbers. So I'm very much a pure mathematician, and so what I really study is things to do with the distribution of primes. So if you're interested in questions to do with patterns in primes, such as primes P, such that 2P plus 1 is prime, a very closely related question is to look at gaps between primes, which is maybe a very fundamental basic problem if you're trying to understand the distribution of any sequence. Trying to understand the gaps that appear in this sequence is one of the most basic ways you can build up a general toolkit for understanding the sequence. So let's try and understand the gaps between prime numbers. What you might hope to do is have so prime numbers are always integers, and so the gap between any pair of consecutive prime numbers is always going to be an integer, and you might hope to have some sort of classification of all gaps of a given size. Now, one of the highlights of mathematics from about 100 years ago was the prime number theorem. This has maybe already been mentioned offhand in Cliff's talk, that if you want to count the number of primes less than some large number x, this is very roughly x divided by log x. And this means that if I'm looking at primes which are of size about x, the average gap between prime numbers is of size about log x. Now, as x gets bigger and bigger, log x gets bigger and bigger, so at least typically the gaps between primes get bigger and bigger and bigger as you go further and further and further down the number line. But just because the average gap gets bigger, it doesn't mean that all gaps necessarily get bigger, and it might be the case that occasionally you get primes that are unusually close together or unusually far apart. So a very natural question is that the case? Can we understand very small gaps between primes, or is it the case that primes always gradually grow like the average gap, or is it the case that sometimes they come clumped unusually close together? And so you might think about trying to go through, and we can first off start thinking about prime gaps of size 1. So this is looking for consecutive pairs of consecutive primes that differ by exactly 1. But we know that if you have any two consecutive whole numbers, one of them must be a multiple of 2, and there's only one prime which is a multiple of 2, which is 2 itself, and so it's easy to see that the pair of primes 2 and 3 is the only pair of primes that have a gap of size 1. So the natural thing to do, so we've therefore classified all prime gaps of size 1. So the next step is to naturally classify all prime gaps of size 2. So you can start looking for prime gaps of size 2, and you start finding that there's quite a lot of them. So 3 and 5, 5 and 7, 11 and 13 are pairs of consecutive primes that differ by exactly 2. as you start going through and looking at them, you can get a computer to just keep on calculating them, you see that these seem to just keep on coming. So the first pair bigger than 1,000 is 1,031, 1,033. The first pair bigger than 1,000,000 is 1,037, 1,039. The first pair bigger than 1,000,000,000 is 1,000,007, 1,000,009. And these seem to just keep on coming. And so the natural conjecture that mathematicians then make is that these should indeed keep on coming, and there should be infinitely many pairs of primes that differ by exactly 2. So unfortunately, this is also a very famous open problem that mathematicians don't know how to solve. In fact, there's debate about it precisely how old it is and whether it goes back to the ancient Greeks or not, but it's certainly one of the most famous problems in mathematics, and we don't know whether there's infinitely many pairs of primes that differ by exactly 2. So this might be quite disheartening if you're someone like me who tries to understand the primes, that we seem to be stuck at the first non-trivial example. But sometimes naive optimism is a way to go forwards, and so let's not worry and just try and think about what happens more generally. So let's just think about what happens for other gaps. So we don't need to necessarily stop at gaps of size 2, even though we don't know how to prove anything. We could think about gaps of size 3, but then gaps of size 3 is basically the same as like with gaps of size 1. You'd have to have one of the two being even, and so 2 and 5 is going to be the only possible gap of size 3. And in general, for any odd size gap, you're going to have this problem to do with multiples of 2, and so there's only at most one pair of primes that could differ by that. But if you start looking for even-sized gaps, not just 2, you find exactly the same thing that we found with 2, that these prime gaps seem to come again and again and again and again, and they come with really a decent frequency. And so not only do we believe that there should be infinitely many pairs of primes that differ by exactly 2, we believe that there should be infinitely many pairs of primes that differ by exactly 4, and infinitely many pairs of primes that differ by exactly 6 and 8, and so on. But you also don't need to stop there. If we're not worried too much about proving things at this stage, we could look at more general patterns of primes clustered very close together. And it turns out that this is generalizing the problem is useful for making progress on the original problem. So you could think about triples of primes that come very close together. And so maybe the most basic example of this would be, can you have triples of primes contained in very short intervals? So primes have to be integers, so they would have to be contained in an interval of length at least 3, but you know that somehow you have to avoid odd ones, and we have the same problem that if you're looking for triples of primes contained in an interval of length 5 or less, then at least one of them has to be a multiple of 3. So 235, 237, 257, and 357 are the only triples contained in an interval of length 5 or less, because one of them has to either be a multiple of 2 or a multiple of 3. However, you can then try and do the same thing for intervals of length 6, and you actually find that there's lots and lots and lots and lots of these patterns. So all of these patterns either look like n plus 2, n plus 6, or n plus 4, n plus 6. But for either of those two different types of patterns, you find that there's just lots and lots and lots of different numerical examples, and so you naturally guess that there should be infinitely many. OK, so if you'll bear with me, we can go for a more general setup that encompasses everything that we've seen before, including the sorts of questions connected to cryptography and Sophie Germain's approach to Fermat's last theorem, because all of these are encapsulated by if I take k different linear functions, so I'm just thinking of functions that send x to ax plus b, where maybe a and b are fixed positive whole numbers. We know that you can't have all of these functions being simultaneously prime, because we know that n and n plus 1 can't be simultaneously prime, apart from when n is 2. And we've seen that that's because of an issue to do with division divisibility by 2, that for every value of n, one of n and n plus 1 is always a multiple of 2, so n times n plus 1, the product, is always a multiple of 2. Similarly, when we were looking at clusters of primes contained in an interval of length 5, it wasn't the case that one was always a multiple of 2, because you can have n plus 2, and n plus 4 all be an odd, but we saw that one of n plus 2, and n plus 4 always has to be a multiple of 3. And so there was a problem to do with divisibility by 3, because for every value of n, the product n times n plus 2 times n plus 4 was always a multiple of 3. And so if you're going to have these k different linear functions that you chose all being simultaneously prime, you need to avoid these obstructions to do with the product always being a multiple of some fixed number. Because then clearly you can't have a product of k primes, all of which are a multiple of 5, or all of which is always a multiple of 7. And so we say your set of linear functions is admissible if you avoid this trivial obstruction about having a fixed prime divisor. So all this means is that there isn't some really obvious way why your linear functions can't be simultaneously prime. And then the conjecture that brings together everything that we've seen so far is that if your set of linear functions avoids this trivial obstruction, then it should indeed be the case that there are infinitely many integers n, such that all of your linear functions are prime at the value n. So choosing your linear functions to be in n and n plus 2 would get back the twin prime conjecture. Choosing your linear functions to be in n and 2n plus 1 would get back the question that we saw connected to Fermat's last theorem and cryptography. If we're looking at n plus 2, and n plus 6, that'll get us back to triples of primes, all contained in an interval of length 6. And this generalizes everything that we've seen before, and this is known as the prime k-tuples conjecture, which is a very far-reaching conjecture to do with these patterns of primes. It's also sort of variations on the prime k-tuples conjecture that lie behind the estimated runtime of factoring algorithms that Cliff mentioned in his slides beforehand. OK, so far maybe I've talked a little bit about why primes are important, that they, whenever there's problems to do with whole numbers being multiplied together, you might hope to reduce it down to a problem about prime numbers. And I've said that when you get involved in these questions about primes, the key aim is to get some general understanding about the distribution of primes. So maybe as a warm-up case, we looked at gap stream primes, and we generalized everything to this far-reaching prime k-tuples conjecture that gives maybe a reasonably comprehensive guess as to when you should have infinitely many primes in certain patterns and when you shouldn't have infinitely many primes in certain patterns. And this fits with all available numerical evidence as well as possible. But as pure mathematicians, we're obviously not satisfied about just coming up with some guess as to whether these answers are true or not. What we would really like to do is to be able to come up with theoretical proof that something like the twin prime conjecture or the prime k-tuples conjecture is indeed true. And that's been a major theme in my research, is studying questions connected to things like the prime k-tuples conjecture. So one easy-to-state headline result that was sort of mentioned in my Fields Medal citation and things like that is work that I've been involved in with various collaborators. This shows that there's infinitely many bounded gap stream primes. So there's infinitely many pairs of primes that differ by no more than 246. So if we remember what I was talking about a few slides ago, we said that if I'm looking at very large primes of size x, the average gap between primes is of size about log x, and so it gets bigger and bigger and bigger. And so even though the average gap grows without any limit, however far down the number line you go, you find these unusual pairs of primes that come unusually close together, and so are clustered at most 246 apart. Now, what we'd really like to do is to replace 246 by 2, because then we'd have proved the twin prime conjecture. Unfortunately, I don't know how to prove the twin prime conjecture, but this was essentially the set of work involving me and other people was the first time we were able to put any number here in place of 246. 246 is not some terribly natural number, it's just something that comes out as an artifact of our method. And our method isn't really about proving results just about bounded gaps between prime numbers, although that's a consequence of it. What we really try and do is prove a weak form of the prime k-tuples conjecture. So if you remember the prime k-tuples conjecture, the idea is that you choose your favorite k-linear functions, and the challenge for me is to show that, provided they're admissible, they are simultaneously prime infinitely often. Now, I don't know how to prove the prime k-tuples conjecture, and I don't know how to, and that's because I don't know how to show that all of the linear functions are simultaneously prime. But you might accept a weak version of the prime k-tuples conjecture, where I don't have to show that all of them are simultaneously prime, but I just have to show that some of them are simultaneously prime. And this is precisely what we do in our work. So for example, one of my results on this shows that I can guarantee that m of your linear functions are simultaneously prime infinitely often, provided you started off with a set of linear functions that's big enough in terms of m. So if you want 2 of your linear functions to be simultaneously prime, it's good enough to choose 105 linear functions. And I can't tell you which pair of linear functions are simultaneously prime infinitely often. And of course, we expect all 105 of them to be simultaneously prime infinitely often. But I can show that at least 2 of them have to be simultaneously prime infinitely often. And so then, to get a result about bounded gaps between primes, you can just choose all your linear functions to be n plus a constant. You have to be a little bit careful about precisely what constants you choose to make sure you don't run into one of these cases of it looking like n and n plus 1, where you have a fixed divisor. But you can choose your constants to make this set of linear functions admissible. And then 2 of these linear functions being simultaneously prime means that those pair of primes, whenever they're simultaneously prime, have to differ by just a bounded amount, because it's always determined just in terms of the shifts that you use in your linear functions. If I could have n and n plus 2 being simultaneously prime, then I'll get the twin prime conjecture that you differ by at most 2. But if I'm saying that 2 out of n plus 2, and n plus 6 are simultaneously prime infinitely often, then I know I'm certainly getting, every time 2 of them are simultaneously prime, I'm getting a pair of primes that differs by at most 6. And so I'm getting bounded gaps between primes. But what we actually show is rather more than just if you have enough, you get 2 of them being simultaneously prime. If you go a little bit further and you have a bigger set of functions, you can have 3 of them being simultaneously prime, or 4 of them, or as many as you like, provided your set is big enough. So this is much weaker than the prime k-tuples conjecture. So I failed to prove the prime k-tuples conjecture, but this is maybe the first important progress towards the prime k-tuples conjecture in terms of making these linear functions simultaneously prime. And our work also very much fits with the heuristic philosophies behind the guess as to why the prime k-tuples conjecture is true. So we, as mathematicians, we don't only believe the prime k-tuples conjecture is true because we looked for twin primes and we seem to find there's quite a lot of them. We also have heuristic theoretical guesses as to precisely how many twin primes there should be, up to some large number, and you can then test these very precise guesses on a computer, and all the numerical evidence fits with our theoretical predictions as well as possible. And even if you're slightly dubious about just looking at finite numbers on a computer, this work is somehow very compatible with the philosophy of that heuristic guess. And so if you have some, say, cryptographic scheme or some way of trying to work on things that relies on the hardness or the easiness of questions to do with the twin prime conjecture, it means that our heuristic guesses maybe have a slightly more solid grounding. OK, so for the remaining bit of my talk, I'd like to talk a little bit to give a flavor of how you might go about proving some of these results about prime k-tuples conjectures and linear functions being simultaneously prime. And one way I like to think about the whole argument is as an application of the probabilistic method. So what I want to do is you've chosen your favorite k-linear functions, and I'm trying to prove that some of them are simultaneously prime infinitely often. So at first, I'm going to choose some very large number x, and I want to choose a number of size x, so maybe a whole number between x and 2x, randomly according to some probability measure. And for this random number between x and 2x, I want to calculate typically how many of my linear functions are simultaneously prime. And if typically I have at least 2 of my linear functions being simultaneously prime, then there certainly must be at least some cases when 2 of them are simultaneously prime. And so if I can show that typically more than one of them is prime when I choose a number between x and 2x for every large value of x, then that means for every large value of x, there must always be some number between x and 2x where 2 of them are simultaneously prime. And this would mean that infinitely often, at least 2 of them are simultaneously prime. Similarly, if I can show that typically you have more than 10 of them being simultaneously prime, then that must mean that at least occasionally 11 of them are simultaneously prime. And so I just need to show that the expected number of the linear functions which are prime is bigger than m if I want to show that at least m plus 1 of them are simultaneously prime. OK, so this is a sketch of the argument, but the natural question then is, OK, how do you choose a good probability measure, and how do you calculate this expectation? And these two questions are actually very closely linked. Because one way that you could choose the probability measure would be say, well, I'll choose n's of size x with equal probability subject to the condition that all my linear functions are simultaneously prime. And in some sense, this would be a very good measure to choose, because that would maximize the expected number of the linear functions which are simultaneously prime. It would be ensuring that all of them are simultaneously prime. Apart from, this is a completely circular argument, because for this to possibly work, it requires me to know that there's at least some value of n for which all the functions are simultaneously prime. And so that would be sort of trying to prove the prime k-tuples conjecture, assume the prime k-tuples conjecture. And in particular, it's impossible to calculate the expectation in that case. On the other hand, a much, much simpler choice would be to just choose my integers n uniformly at random between x and 2x and not have any particular preference for any value of n over any other value of n. But unfortunately, we saw from the prime number theorem that the primes have density 1 over log x. And that means that if I have k-linear functions, typically I would expect k divided by log x of them to be simultaneously prime. And so when x is very large, this is less than 1 of them being simultaneously prime. And I completely failed to prove that 2 of them are simultaneously prime. And so what I'd really want to do is to choose some probability measure that's in between these two extreme examples, that has some of the simplicity of just choosing all numbers equally likely, that means I can actually calculate everything, but has some of the complexity of the condition of making the linear function simultaneously prime, so it is actually capturing the arithmetic of what's going on. And so then the question is, how do I choose this probability measure that's simultaneously concentrated on integers n when many of the linear functions are simultaneously prime, but at the same time is easy enough to actually be able to use mathematical unconditional mathematical techniques to calculate these sorts of expectations. And there's a whole area of sieve methods, which is one of the topics in mathematics that I work on a lot, is one of my particular focuses. And you can think of sieve methods as precisely trying to come up with things that go between the complexity of the primes and the simplicity of the integers. So for lots of the sorts of questions about patterns, if I ask the same question about the integers, it's just very easy. Are there infinitely many integers that differ by 2? Well, yes, obviously, and I can count them very easily. But the question becomes very difficult with primes, and so I would like to have something that interpolates between the integers and the primes, captures some of the arithmetic complexity of the primes, but still has the fact that it's similar to the integers in that I can actually calculate things using unconditional techniques. And this is what we sometimes call almost primes, and you can think of giving every whole number a score based on how prime it is, according to some simple scoring rule. So the precise definition actually depends an awful lot from context to context, and so maybe I don't want to go into too many details, but you could imagine I want to give a low score to numbers that have, say, very small prime factors. If you're a multiple of 2, it's very easy for me to detect that you're a multiple of 2, and I therefore want to give you a very low score because you're clearly not a prime number. But maybe it's very difficult for me to distinguish between RSA-type numbers, which are products of 2 similar-sized primes, but I don't need to perfectly distinguish between them, so maybe they will be pretty close to being prime, and they can still have a high score, but I'm still capturing some of the complexity of the primes. So it turns out that it's still a little bit more of an art than a science, precisely what sort of sieve method you should use in what sort of situation, which corresponds to what precise definition of almost prime you should use in each situation. But some key properties that are sort of uniform across all reasonable definitions of almost primes is that they have similar overall statistical properties to the prime numbers. So these weighted integers typically will have no very small prime factors because you'll put a very low weight on numbers that are a multiple of 2 or 3 or some other small prime. They'll have similar distributional properties, so they'll have similar distributions in arithmetic progressions or in short intervals. And then there's 2 absolutely vital properties. The first property is that almost primes somehow capture a lot of the arithmetic essence of the prime numbers. So prime numbers always have weight 1, and the total weight of the primes is a positive proportion of the total weight of all numbers that are given. So this means if I choose a number according to how almost prime it is, I'm not necessarily guaranteeing that I get a prime number, but I have a positive probability, maybe 20%, that I get a prime out at the end. So it's sort of 20% of the way to being a prime number. And the other key property is that they're simple to calculate with. So they're not quite as simple to calculate with as the whole numbers, but it turns out that you can define scoring functions that only depend on the small divisors of the number in question. And if you restrict yourself to a certain class of scoring functions that only depend on the small divisors, then you can calculate patterns in almost primes using unconditional techniques. And the technical aspect of this is if you have sufficient understanding of your set in arithmetic progressions, then you can understand the almost prime analog of your question. So how would this work going back if we now use almost primes in this probabilistic method? Well, we can define a weight on an integer n based on this how approximately prime all of our linear functions L1 of n up to Lk of n are simultaneously. So this should give a high weight to numbers n when all of our linear functions are simultaneously prime. It should always give a weight 1 to those, and it'll give a low weight to numbers where the linear functions are not simultaneously prime. And so, because I have this scoring function, I can choose my random probability proportional to this sieve weight, this scoring function. And I can now calculate everything, provided I can understand everything in arithmetic progressions. So I can check that this is a genuine distribution, provided I can understand integers in arithmetic progressions, which isn't too difficult. And I can calculate the probability that any given one of my linear functions is a prime, provided I can understand primes in arithmetic progressions. But some of the earlier work on primes, which is now very well known and standard in the subject, has established that primes are reasonably well understood in arithmetic progressions. So this was a big part of the work of Enrico Bombieri, who won the Fields Medal for his work on prime numbers many years ago. But because I can calculate the probability that any one of the linear functions is prime, I can calculate the expected number of these linear functions are prime. And in particular, I sort of declare success and I prove bounded gaps between primes if I can calculate this expectation, and this expectation is bigger than 1 for every large value of x. Now, you might be a little bit skeptical at this point, because if I chose the uniform distribution, we knew that this expectation was getting closer and closer to 0, and so was guaranteed to fail. But because the primes have a positive weight inside the almost primes, that corresponds to meaning that this expectation is not going to go to 0. It's going to tend to some constant as x gets larger and larger. And so there's some constant that depends on my precise definition of almost prime, and I can calculate this constant whenever, as x gets larger and larger, my expectation is going to tend towards this constant, which means that I've won if this constant is bigger than 1, but I haven't proven anything at all if this constant is less than 1. So unfortunately, things then get a little bit technical and messy because the value of this constant depends on the precise definition of almost prime. And this precise definition of almost prime depends on how well we understand primes in arithmetic progressions. And unfortunately, lots of the standard off-the-shelf sieves you can run through this whole argument, but they give a constant which is less than 1. And so the whole argument fails. So the question then becomes a very delicate question about the precise definition of almost prime. And there's a sort of natural choice that's optimal in lots of situations. And if you go through all of these very technical mathematical calculations, it turns out this standard choice gives a constant 1/2, and so the whole method completely fails. And so this is pretty depressing. You've come up with this whole method for trying to detect bounded gaps between primes. You do all these complicated theoretical calculations based on primes and arithmetic progressions. You come up with this idea of using almost primes, and then you come up with a result that's 1/2, which is less than 1, and the whole method's failed and give nothing. There was then a breakthrough by Golson-Pinson and Theorem, who came up with a different definition of almost prime, and this improved the matter by a factor of almost 2. So the constant essentially became equal to 1. Unfortunately, it was always just less than 1, so I said for every large value of x, it's approaching a value, so it's approaching 1 from below, and so it always just failed. But unlike before, when we were failing by a huge amount, now we're only failing by a whisker. And so it was really tantalizing. And then Yitang Zhang came along, and he proved a technical result about primes in arithmetic progressions that was slightly better than what we did before. And so The consequence of Yiteng Zhang's work was that he was able to then tweak the definition of almost prime, and he was able to improve the constant very slightly. So he was able to improve it from something just below 1 to something just above 1, but that was enough in principle to prove bounded gaps between primes. And the key contribution that I made was a different choice definition of almost prime that was very much tailored to this problem, that gave a constant that gradually tended to infinity as you were looking at more and more and more linear functions. And so, in particular, if k is large, the constant was about 1/4 of log k, and this is what ended up giving a result that says that you can have m of your functions being simultaneously prime, provided you chose k to be sufficiently large in terms of m. So just to give a sort of sketch overview, we wanted to prove a result about small gaps between primes, maybe bounded gaps between primes, or weak versions of the prime k-tuples conjecture. And the key thing that we're using here is a Sieve method to give this scoring of almost primes, a score for how approximately prime an integer is. And as a basic input, you need to use technical results about primes and arithmetic progressions. And once you have this set up, it turns out that there's a few interesting different subproblems, a combinatorial problem about how tightly you can pack your linear functions, and an optimization problem to do with smooth functions. But the key point is that the Sieve method is turning results about primes and arithmetic progressions into results about small gaps between primes. And the original Sieve methods were a little bit too weak to do this. Yiteng Zhang's result was improving the arithmetic input into the whole method, and that fed through to give a stronger result on the right-hand side, whereas my modification was the Sieve method at the heart of this translation. But if you see a result of this type, and you see that Yiteng Zhang gets slightly better results by feeding in better information, a natural question is, well, how far can these methods go? Can you maybe prove the twin prime conjecture if only you had stronger results about primes and arithmetic progressions? If you are willing to assume the most optimistic results about primes and arithmetic progressions, what's the real limit of these techniques? So unfortunately, there's a hard barrier to our techniques that means that these techniques can't prove the twin prime conjecture on their own. Roughly, this corresponds to the primes can have at most density 1/2 in the almost primes, because for any reasonable definition of almost prime, they have to give the same weight to numbers with an even number of prime factors and numbers with an odd number of prime factors. And so even if the odd number of prime factors numbers were really concentrated just in primes, which sometimes you can make happen, it can have at most density 1/2. So you can't possibly prove that if you have two linear functions, they're both simultaneously prime. But maybe the next best thing would be to say, if I had 3 linear functions, I can show that at least 2 of them are simultaneously prime. And in work with collaborators, we were able to prove precisely this. So there's a technical conjecture known as the generalized Elliott-Halberstam conjecture that I've written as GEH here, which is a technical result claim about primes in arithmetic progressions that we believe to be true, but is outside of what we know how to prove. But if you believe this technical result about primes in arithmetic progressions, you get a souped-up version of our method, and then we are able to prove that there's infinitely many pairs of primes that differ by at most 6, precisely by saying whenever you have 3 linear functions that are admissible, at least 2 of them must be simultaneously prime infinitely often, and then you can just choose your 3 linear functions to be n plus 2, and n plus 6. But because we can't do 2 linear functions out of 2, we can only do 2 out of 3, this is a hard limit to our methods without some new ideas. But it turns out there's also a sort of slightly amusing other consequence of this. So along with the twin prime conjecture, another very famous conjecture in mathematics that's been open for hundreds of years is Goldbach's conjecture that claims every large even number can be written as the sum of two primes. And we don't know how to prove the twin prime conjecture, and we don't know how to prove Goldbach's conjecture. But one amusing consequence of our work was that if you assume this technical result about primes and arithmetic progressions, then either the twin prime conjecture is true, or Goldbach's conjecture is almost true, in the sense that every large even number is very close to a number which is the sum of two primes, is within 2 of a number that's the sum of two primes. So of course we expect both of these statements to be true. We can't prove that either one of them is true, but we know that they can't both be false. So either if there are not infinitely many twin primes in some bizarre alternative universe, then Goldbach's conjecture is at least almost true. And so the key point here is maybe that we have a new way of looking at prime numbers by these new ways of defining almost primes to interpolate between easy questions to do with integers and difficult questions to do with prime numbers. And this is fortunately a very flexible method that can apply to very general patterns, and sort of I view it as hopefully a first step towards kind of much more significant progress on trying to understand these general questions and developing a general toolkit for trying to understand the distribution of primes. In a few special situations, mathematicians are able to combine ideas based on this approximate prime numbers and almost primes with some extra arithmetic information to not only prove some of these weak results, but actually calculate directly with primes on the nose. That somehow it's very important to get halfway there with almost primes, and then you incorporate some extra arithmetic information to really allow you to answer the full original question to do with prime numbers. And so I feel that that's the most important, outstanding question in this sort of area. If you want to prove the twin prime conjecture, for example, there are these technical extra bits of arithmetic information known as type 2 results, that if you could prove them, then you would be able to prove the twin prime conjecture precisely by piggybacking on top of this definition of almost prime to get into the primes themselves. In simpler cases than the twin prime conjecture, we do know how to do this. We don't know how to do it for the twin prime conjecture itself, but that's a challenge for maybe the next generation of mathematicians. I think I'm almost out of time now, so maybe I'll stop here. Thanks a lot for listening. I hope you enjoyed the talk.